Welcome back to the Signals and Systems class. My name is Jong Park. Okay, we will continue the stuff we did in the last lecture, which was about the continuous time sinusoidal signal. We are now dealing with chapter 2. The first chapter was about the introduction of this course, and now we are talking about some basic signals. After talking about basic signals, then we'll talk about some systems. The first one was about the sinusoidal signal, which can be represented as the amplitude right here times cosine or sine, it does not matter. So I will write cosine here for our the first equation. And then cosine of the omega t plus phi, where omega is called frequency and phi is called phase. And frequency has two units, which are hertz and radian per second. Since radian has no unit at all, then you can represent this as s to the minus 1. And between these two units, you have to convert it with the equation A. And sometimes there is a confusion about the hertz and the radian per second, so I think you should really memorize or think about this equation. So 2 hertz means like 2 cycles per second, and 1 cycle is equivalent to 360 degrees, 1 whole cycle. So 1 whole cycle is it means 360 degrees, which is also equal to 2 phi. That's why 1 cycle, if you want to convert this to the radian, then you have to multiply by 360 degrees, and not in degree form, but in radian form, you have to multiply it by 2 phi. And since inside this parenthesis, you want to have the unit of radian, and so when you want to import this frequency information into this equation, you have to convert it into the radian per second unit. Therefore, you cannot just bring 2 into the omega, but you have to change its unit into the radian per second by using this equation A. So this is not true, common mistakes, but you have to go like this. And since this is radian per second, if you multiply radian per second by second, you get radian. And if phi is represented in radian form, then you can successfully add these together to get the cosine value. Okay, so I think this is enough about the hertz and radian per second. And now I would like to talk about some stuff. Okay, and about the phase. Phase represents the transition of this sine wave or cosine wave. So depending on the value of phase, the signal can be like this. Okay, so if phi is 0, then the very top here would be the origin. It will cross the origin, but if we have some phi, then you have to be not like this, but with some value of phi, you may go like this, or you may go like this. And if this is the case, representative figure, then what's the value of this? What's the value at the origin? T equals 0. You just put t equals 0 into this equation and you get a times cosine phi. Yes. It's obvious. And I would like to talk about some properties of the sinusoidal signal. The first one is about the periodic. So there is x of t, and this x of t, so the periodic means if you shift some amount along the time axis, then the signal repeats itself. By expressing that statement into the equation, if you shift the time, the x-axis, by some amount, and I will say that amount as t large T0. So if you shift time axis with some amount, then the signal repeats itself, which means it has the same value of it has the same value of the signal. And the periodic refers to this equation, and if you put these equation into our sinusoidal signal equation, then the left-hand side is just this one, so it goes like this. And with the right-hand side, you have to put t plus large T0 into the t. Then you get this kind of equation. And if you want to remove the parenthesis inside the cosine, then you can get this equation. At this point, in fact, you already know about the sine wave or cosine wave, generally sinusoidal wave. If you shift the sinusoidal wave by 2 pi times m, where m is an integer, then you get the same value. You get the same signal. Okay. You already know that. With like 2 pi or 4 pi or 6 pi, 6 times pi, in the negative part, minus 2 times an integer, you can get the same function. So with that kind of fact, we can say that this omega 0 times t0 equals 2 pi plus, 2 pi times m, where m is an integer, then the right hand side and the left hand side becomes equivalent. So this part right here equals 2 pi times m, where m is an integer referring 정수. Then you can get the same signal, same result, same value. Therefore, with this equation, you can say that t0, large t0, equals 2 pi m divided by omega 0, and period. So this is so we are talking about the periodic property, and we can define period as the smallest value of t0. So this is a definition. And if you want to get the smallest value, you have to, how do we deal with m? M is an integer, and if you want to be the smallest value, m must equal 1, right? So you can say it's 2 pi over omega 0, which is a period. So the smallest value which repeats itself, you can see in this figure, is obviously this much. So you can refer to this as t0 as in our equation, which is 2 pi over omega 0. And with this equation, with the relation between Hertz and radian per second, which we talked about at the beginning of this movie, you can say omega is 2 pi times f, and if you substitute this equation into this equation, then you can also say t0, the period is 1 over f. You can also say that. Okay? You just substitute omega equals 2 pi times f, and you can get the 1 over f as a period. So this was an example. In Korean, the period means 주기. Okay. And some other properties include the time shift, the relationship between the time shift and the phase change. we already have an experience with the time shift, which we have already done here to see to examine the property of a periodicness. We do the same thing with the sinusoidal shift, and this time we will use small t0 for the time shift. And the signal becomes, so if we think of, if we think of the sinusoidal signal without the phi here, and imagine that we just have a times cosine omega t, and with that equation, if you substitute t as t plus t0, then it becomes this equation. By solving the parentheses inside the cosine, we can get this equation. And if you refer this term as phi, then it becomes the original equation we already had. And there is no restriction about defining this whole thing as phi. Therefore, time shift means phase change. You can interpret that as a phase change. In other words, shifting t0, shifting time axis as amount of t0 equals the phase change of omega 0 times t0. So it is equivalent. And also, can we do the opposite? Like from the phase change, does it also mean the time shift? Exactly. So performing the phase change also means the time shift in continuous time sinusoidal signal. Eventually, both ways are possible. And as we move further, you can see that both directions are not possible with some signal, which is a discrete time sinusoidal signal. We will see it soon, but we will stick here with the continuous time sinusoidal signal. And in a few moments, you will see that this both direction is not possible with discrete time signals. With continuous time sinusoidal signal, there are some signals which are even. And with our cosine signal, if you put phi as 0, then the equation becomes a times cosine omega 0 t times t, and this is an even function. The definition of even function is as follows. So xt equals x of minus t. So if you put minus t in the position of t, the time argument, then even though you switch the sign to all the t's that you have, the result is, if the result is same, then you can call that an even function. So the cosine wave is the most famous even function. Cosine wave, cosine signal is the most famous one, and you can geometrically you can say that even function is symmetric with respect to the y-axis. Okay, so if you call this x-axis, which is a timeline, and the y-axis, which shows the value of the signal, then even function can be seen as the symmetric with respect to the y-axis, which means if you fold this signal with respect to y-axis, then you get the same value. Okay, so the opposite word of even is odd, but before we enter the properties of an odd function, what happens if we shift this signal as an amount of minus phi over 2 phase shift? Then so this was an original signal, and if we do the phase shift with an amount of minus phi over 2, then you get the equation of a cosine omega 0 t plus phi, but we know that phi is equal to this amount, so we replace the term phi to minus phi over 2. And we had the equation of cosine here. Okay, and this is one period, and so in terms of phase change or phase shift, you can say that minus pi over 2 is a quarter of 2 pi, and 2 pi is 360 degrees, which means one whole cycle. So we can say that by shifting the phase over minus phi over 2 means we are shifting the whole signal an amount of quarter, which means 1 over 4. Like 1/4 part of the signal will shift to the right side. Therefore, in terms of phase shift, we can say that this amount is 25% part, a quarter, and another quarter, and the third quarter, and the last quarter. So each of these refers to a quarter of the whole cycle. So as minus 5 over 2 is a quarter of 2 pi, we shift the original signal as a quarter amount to the right side. Please think of the direction. Why do I have to go to the right side? Not to the left side. Okay. You can figure out that. As the phase shift is done, and if you connect the continuous signal to both directions, then what kind of sinusoidal wave do you obtain? This is a sine wave. So the cosine wave becomes sine wave by shifting the phase over 1 over 4 part, a quarter part of a total cycle. So this becomes A times sine of omega 0 t. And we can also prove this with a mathematical relationship. About the cosine. Only by using this equation. So please note that we have a relationship. I would like to introduce two of them. Sine of A plus B is sine A times cosine B plus cosine A times sine B. And also, with a cosine of A minus B, this can be seen as cosine A times cosine B plus sine A times sine B. And if you want to prove this, if you want to see the proof, and refer to some basic mathematical textbook and you will find it. And I'm not going to go through the whole proof right now. And I will use the second equation here with this, the result of the phase shift. Then what do we have as A, the omega 0 t, and B as plus phi over 2? Is it correct? So if you put this equation into this one, then so cosine omega t, cosine of pi over 2 plus sine omega 0 t times sine 2 pi over pi over 2, excuse me. You can get this equation, and you know that cosine of 90 degrees equals 0. So you get this whole term removed, and you can say that sine of 90 degrees equals 1. Therefore, you get large A times sine of omega 0 times t. And obviously, you get the same answer here. So you can prove it via the relationship, these relationship, and also you can see it as the phase shift to produce the same result. And finally, as we already learned that phase shift also means time shift, we can view this equation as a time shift. So to do that, we make a small parenthesis inside the cosine, and you can bring omega 0 out of the new parenthesis, and you get t minus pi over 2 omega 0. And obviously these are the same equation. And you have to recall a period equals 2 pi over omega 0, which means omega 0 is 2 pi over t0, and we will insert this relationship into the omega 0 in the denominator, which will bring a cosine of omega 0 t, and it'll become minus large T0 over 4. So what does this equation mean? It means it shifts a times cosine omega t to the right part as of like how much amount? A quarter of the period. So you can say that the phase change in continuous time sinusoidal signal also refers to, so I'll change the line, time shift. You can always say that. So like this kind of time shift, this kind of phase shift also refers to the time shift as a quarter of the period. So we are talking about the exact same thing in terms of phase shift, and in terms of some formula, and in terms of the time shift. Okay, so that you can you can have like multiple views in terms of the same result. Okay. Even though it is very easy, you want to distinguish between the phase shift and the time shift here. I know it's just about making the inner parenthesis inside to make this as a time unit, but please think about the meaning, because even though this is very easy example, it means like about the relationship between the phase shift and the time shift, and both ways are possible for the continuous time. Lastly, we have an odd function. So there's an odd function among some sinusoidal wave. I think I missed function here too. So there are even function and odd function, and for even function we have this kind of definition, and the odd function's definition is as follows. So x of t equals minus x of minus t. So this is the only difference between the even function and the odd function. So the most famous odd function is a sine wave. So if you look at the sine wave, do you see some symmetric property? In terms of even function, the signal was symmetric with respect to the y-axis. What about for the odd function? So the odd function, it is symmetric with respect to the origin. To do that, if you fold twice, once for the y-axis and then for the x-axis, you get the same value. So if I fold the left-hand side of this signal with respect to the y-axis, then you get this part here. And if you fold again with respect to the x-axis, which means symmetric against the origin, then you get exactly the same signal, and this means an odd function. So there are even functions and odd functions among the continuous time sinusoidal signal. And now I would like to move on to the discrete time sinusoidal signal. As I mentioned in the introduction chapter, discrete time, you only deal with the integer value of input. So we express the discrete time sinusoidal signal with the square bracket. We always use the parenthesis, which is a round bracket for the continuous time. And for discrete time, we will use the square bracket with the right angle here. And we will distinguish between continuous time and distinguished time in equations for the whole lecture, okay, for the whole semester. And for consistency, I will choose the cosine again. So A times cosine, and then we will use large omega. The uppercase form of the omega is like this. So this was a small, like, this was like a lowercase for the omega Greek letter, and this is an uppercase for the omega. So we will use uppercase frequently for the discrete time sinusoidal signals, so you can distinguish these two. And we will not use the letter T, but we will use N for an input of the discrete time signal. And phi is the same. So the most important part for the discrete time, that this is an integer. For T, you can have whatever you want. You can have 1, like 1.2 or something like that as a continuous signal, but for discrete time, you can only have an integer for the input of the signal. So this one is exactly same as continuous time sinusoidal signal, that if you define 3 parameters, A, large omega, and phi, then you can totally describe a discrete time sinusoidal signal. So the definitions are the same, but I'll repeat again. A was an amplitude. Large phi is also a frequency. You don't have to write this down because you already had it in the continuous time signal. And phi is called phase. So I would like to import some images because I don't want to draw them. And I already uploaded these figures here on the AjuBB Blackboard, so you can download it. So I'm gonna import some figures during the lecture, as I already mentioned, which I don't want to draw, and also I don't want to draw some complex figures because I have terrible drawing skill. 여기 있는 그림들은 제가 자료실에 아마 이미 업로드를 해놔서 필요하시면은 거기 나와 있는 PDF를 다운받으셔서 그림들 같이 보시면서 수업 따라오시면은 좋을 것 같습니다. So here are some examples, and I want to rewrite the definition here for comparing to get what kind of value does it have as a large omega 0. So the upper example, you have what's the omega 0 for the upper example? Two pi over 12, maybe pi over 6, it's correct, and you have a phase of 0. And with the lower part of an example, you have an 8 times pi over 31 as a omega 0 and no phase change. And also if you compare to the continuous time sinusoidal signal, you only have the values at integer part. Okay, so there are no values between the integer, so you only have the integer part for the discrete time signal case. Okay. And I would like to talk about the time shift, the relationship between the time shift and the phase change for the discrete time sinusoidal signal, to see if both ways are possible, or maybe one way or none. So the time shift and the phase shift or the phase change does not matter. With the continuous time case, we had the both ways okay. So if you shift the discrete time side to sinusoidal signal by the amount of n0, then we can write down that as omega 0 times n plus n0. Is it okay? Assuming that phi is 0 at the for this example here, then you can solve the inner parenthesis and get phi 0 times n plus omega 0 times n plus omega 0 n0. And as we already did in the continuous time case, we can define this as a phi, and obviously we can say that shifting the time can be seen as shifting the phase. So we have this way as a true. However, so this is the important part. However, if you do the phase change first, so if you change the phase for like a random value, can you convert this random value of phase change to make that as omega 0 times n0? We have a additional restriction in the discrete time sinusoidal signal, that n0 must be integer. So if you change the phase like with the amount of with a random value or the amount you want, then there is no guarantee that this can be an integer, because with a signal, if you have the discrete time signal, then you already have the omega 0 as some value. This is already determined. The omega 0 is determined. Then the phase you change must equal to the omega 0 times the integer. But there's no guarantee if you produce this amount, whatever you want. Therefore, the opposite way is not true for the discrete time sinusoidal signal. if you do the time shift first, then you will obviously insert some integer like -1, -100, or 12, or 1012. Then you can get the result of the phase change, and there's no restriction. But if you do the phase change first, then there's no guarantee that this equation is always true for an integer n0. You cannot guarantee that n is an integer. Okay, so the difference between the continuous time and the discrete time then is the direction of the phase shift and the time shift. Even function and odd function also exist for the discrete time, and I will move this part fast. So even function, we have the same definition, but only with the difference of the bracket form. So it's the same. And the odd function also has the same definition. So, I mean, even though in discrete time signal, even function and odd function also exist. Excuse me. And let's talk about the periodic. In continuous time, every sinusoidal function is periodic, but in discrete time, it is not. So we will begin with the definition, which is the same one as in the continuous time. So the definition was like xn should be, the signal should be repeated over n plus large N, where n should be a smallest integer for a periodic, for the period to be defined. So as we already did in the continuous time, we will equivalently insert this relationship into the sinusoidal wave form. So we will substitute this relation into this one, and the left-hand side will be the original equation, whereas the right-hand side would be like this. And as you already know, then the left-hand side and the right-hand side is equivalent only if this part right here equals to 2 pi times m, where m is another integer. Okay, we already had this relationship. And this means that large omega 0 times large n equals 2 pi times m. And here, the large n is a period, so if we organize this equation with respect to large n, then large n should be 2 pi times m over large omega 0. So, if you think about this equation, then m has to be an integer, and also large n has to be an integer. So both large m and small m need to be integers. And so let's find out with some examples that if this is true for every discrete time signal, or some of them are true. And I would like to use this figure for one more time. With the first example, we already know that omega 0 was 2 pi over 12. Therefore, if we substitute this answer into this equation, then large n, a candidate for a period, will become 2 pi times m over, and if we substitute large omega 0 as this value, then you get 2 pi over 12 in the denominator. And if you do the math, you will get 12 times m. And please note that m should be integer, and also large n should be integer. And with this example, with this pretty example, m being 1 gives n 12, which is the smallest integer possible for the first example, and it is period. Okay, so the first example here is, you can say that this signal is periodic. So the first example is periodic, with period being 12. So the period is 12. And let's do the same thing with the second example. So the second example, we have large omega 0 as 8 pi over 31. Then if we obtained large n with the same relationship, then it will become m 2 pi over 31 in the denominator. Then if you do the math, the phi gets cancelled, and I think you will get 31 over 4 times m. So please recall that small m and large n both need to be integers, and if you put m as 1, then large n becomes 31 over 4, which is not an integer. If you put m as 2, it's not an integer, so the smallest integer which makes large m an integer is 4, correct? So if you put 4 as the value of m, then n becomes 31, and this signal is also periodic. So it is wrong if you say that this signal is periodic with a period of 31/4, then this is you get nothing from that question. But you have to say the signal is periodic with a period of 31. Then it is correct because the large n should be an integer. So these two examples, we have a periodic signal, and let's see the third example. The third example is xn equals cosine of n over 6. So what is the omega 0 for this equation? So if you think of this this basic equation here, then omega 0 is 1/6. Is that correct? So if we obtained large n, then you will get 2 pi m over 1/6. So this becomes 12 times pi times m, where m should be an integer and large n should be also integer. So if you compare the third equation with the previous two, then there exists pi in the equation of large n, excuse me. I mean, there's a pi here. It is not cancelled. And you know that pi is an irrational number. Pi is an irrational number. Therefore, no matter what m you can get as an integer, like no matter how big or no matter how small it is, you cannot. It is impossible to make large n an integer. So it is impossible to make an integer period value, and therefore this function here, this signal is not periodic. Okay, so we have this kind of difference. So in discrete time signal, not all the signals are periodic. That was the main point. And I would like to compare some facts between the continuous time and the discrete time sinusoidal signal. So the left part is the continuous time, and the right part is a discrete time. You can distinguish them by reviewing the notation, as I have told you for many times. So the first one is that For continuous signal, the signals are obviously distinct for distinct values of omega 0. Whereas for discrete time, it is identical signals for values of the large omega 0 separated by 2 pi. What it means by this is that if one signal has a frequency of omega 1 and another one with the frequency of omega 2, if omega 1 is not omega 2, so if the values are different, then the signals are obviously different. I mean, if they have different values, then it is done, and there are different signals. There are indeed two distinct signals. So like, if the first one has this signal with the omega 1, and the second one with maybe faster signal with the larger frequency, then they are different signals. As you can see, you cannot match them. But with the distinct signal, let's say we have x1 and x2 with omega 1 and omega 2 respectively, then if omega 1 and omega 2, large omega 1 and large omega 2 are separated by like 2 pi, so if you express this sentence into the equation, if omega 2 equals omega 1 plus 2 pi m, so separated by 2 pi times an integer, this is an integer, then we can modify this equation as follows. So if you insert this value into the large omega 2, and then you can get this equation. And since m is an integer and n is an integer, this value is the multiplication of 2 pi times 2 pi and an integer. Therefore, with the property of the sinusoidal wave, this can be cancelled. And we can express this term to this one, which is equivalent to the first signal. Therefore, you can say that the signals are identical with the frequency separation of the multiplication of integer and 2 pi. So it is very different from, this is one different aspect, and the second one is for the continuous time. Then you can say the signal is periodic for any choice of omega 0. So it's always a periodic signal for continuous time. However, in discrete time, it is periodic, as we have just observed from the examples, 3 examples. It is periodic only if the large omega 0 equals 2 pi m over large n. For some integers n and m. This is the restriction. So both need to be integer, and for a period value, we talk about a positive value. So n should be positive. So the period, if you say that what's a period for that signal, then you have to answer that by the positive number. So n and m should be integer, with n being positive. So if we think about this equation about the period of the discrete time case, and with this kind of description, the signal in discrete time is period only if the large omega 0 has the relationship of this amount. So if we insert this into this equation, which we can express like this, then we can get just n, which is a integer. So with only this period, with only this value, with the value of this kind, this much, the discrete time signal is periodic. So you can compare these two kind of facts for the continuous time. And I think this is all for the sinusoidal signal. And in the next lecture, we will talk about the exponential terms for both continuous time and discrete time. So if you have any questions, please let me know by asking it via by email. Right? You can always ask me in Korean. 질문하실 때는 한국말로 하셔도 아무 상관없으니까 질문을 해주시면은 제가 최대한 빨리 답변을 드릴 수 있도록 노력하겠습니다. So I think this is it for today. Thank you very much for your attention.